once again, welcome back, and it's going to be a real treat to listen to Henri. Not very many people know that he's an architect with incredible practical experience. It's actually possible for that to happen. So my nickname for him is a Renaissance man, where he has the principles and the theories with the practical experience. I've learned more from Henri than he's learned from me, and I am still learning. So please give a warm, deserved welcome to Henri Fennell.
Thank you, Joe. So Joe called me from Colorado and said they have a lot of SIP failures out here. What's going on? And I said, it's all about the joints. And he said, you're speaking at summer camp. So that's how I got here. So, so I'm just background. I'm old, and this was my first SIP project in 1974. And this was back in the Buckminster Fuller days, and this is the Mekon Master Solid, according to Buckminster Fuller. And one of my classmates in college and I put together this jig in the lower right corner here and said, we're going to make SIPs and build a Master Solid with it. And this was my first SIP project in '74. So. Before most of you were born, not all of you, but. Okay, and this was when we started a business making SIPs, and this is metal SIPs. These are standing seam panels on pedestrian footways. This was in '75, and we started a little business making structural insulated panels with metal skins. These are galvanized steel. And these are some other ones on a school in Mattapan. This is in Boston, so that's where we first started, so close to here. And the panels on the penthouse and the panels on the walls here were panels we made in Southie. And these are some scrap panels that are left over. This is the grandkids. And I put that together in 1970. Those panels were made in '75 and they're still going strong. So it's a durable system. And this was we actually started putting solar collectors into the SIPs so that we were collecting energy and saving energy at the same time. This was the poster project for the first NESE conference in Connecticut. And this building had, these collectors are compound parabolic concentrators. So we were actually generating the data in the top left corner here is different tests we had done at the University of Connecticut on these collectors. And we were generating temperatures as high as we were making steam and running absorption chillers so we could do cooling and heating before PVs. This was way before PVs. Today, I would say put the PVs on the target of these CPCs, and we will have a great combination of electric and thermal collection capabilities. And we were using selective black, and we had evacuated targets. So fairly high tech. This is that building. There's Governor Dukakis. If you're from the Boston area, you're old enough to know. I know Joe knows who he was, but anyway, he was making political hay on this. So anybody who doesn't know what a CPC, a compound parabolic concentrator is, this allows the collectors to collect energy with clouds. So this had a target range like this, not a target range like this. And this is This was a patented geometry based on the eye of a crab. Just so you'll know. Anyway, that's not relevant to the talk, but anyway. So what are SIPs? SIPs are a foam core, 2 sheets of sheathing, one on each, usually one on each side. If it's only on one side, it's called nail base. And that's foam with a skin on it that you can nail the shingles to, or the clapboards, or whatever it's being used for. The only thing that's not shown here is there's glue between this OSB and the foam in this particular design, but the other way to do this is to foam it in place. So I was making the SIPs that I made by putting 2 sheets of steel or whatever the material was in a press or a mold, injecting foam between them, and that makes a natural bond, which is based on the research I did at Carnegie Mellon, where I went to architectural school. Thanks for letting that out, Joe. I appreciate it. It's actually a stronger bond than any of the glues that we tested at that time about making SIPs. I thought I heard something. Okay, so you take 2 skins, don't put any, that's the top and bottom of the I-beam. You have the top is in compression, the bottom's in tension, and the web is in shear. And that keeps those 2 surfaces in position with respect to each other, and that's how a beam works. So a stretch skin panel is just like a million little I-beams side by side, and the flange is the foam. So the shear strength of the foam and the bond to the skins is what makes structural insulated panels. It's what determines their ability to span from one support to the next. And of course, the depth of the beam is the other piece of that. So, so how are they made? Take the two pieces of foam, you put the core is either glued to or foamed in place between them. And the length of the spin, I just covered this, nail base only has 1, and a nail base panel has insulation with the sheathing on one side, and that has to be fully supported. So here's a picture of 2 products. These are all made with expanded polystyrene, but you can buy them with polyiso and other kinds of foam. So there are options out there. And one of the things about SIPs compared to spray foam is that SIPs are made in a factory under quality control conditions year-round. You can buy a SIP in the winter that was made in warm conditions and know that it has good quality, and then you can install it at your convenience. And I did lots of, I made custom panels, and I installed factory-made panels depending on the client's requirements. So, and this is Joe actually holding a piece of vented nail-based panel. So those are glued up. That's a piece of polyiso with a thin slice of polyiso that act as a spacer behind the nail base OSB. This is another example of what you can do. Sometimes people will put, this is actually wormy chestnut, and they will put that on top of the frame and then put a SIP on top of it or nail base on top of it. These particular ones, we made these custom for the client, and we attached the inside finish to the panel before it went in place. This is what a crimp machine looks like. This is continuous reaction injection molding process, and this, you lay the OSB on the bottom track, Then you lay the second sheet on top with the foam squirted in between. The foam rises up and pushes against the upper track, and it makes, out of the end comes the panels. So the longest of these that I know of that were ever available, I think were 24 feet long, but it had to do with the limitations of how long you could buy OSB. The advantage of OSB, we started out making plywood ones. The problem was that plywood makes potato chips shapes, and they don't stay flat, where OSB is manufactured and does stay flat. On the bottom right of this slide is a quality control monitor for factory processed polyurethane foam, and that tells you what the ratio is, what the temperature of the chemicals are, the temperature of the platen, the ambient temperature, and so forth, and it turns the machine off if any of those go out of spec. That's what doesn't happen in the field in all cases, depends on your equipment. So what are they made of? You can have skins made of drywall, manufactured wood, steel, aluminum, and the key there, we made some, the ones that we showed in the barn were made of thermoplastic. Norel is what they were made of. That's what the seats in an airplane, commercial airplane, are made of. And that's what those particular panels had as skins. So that was a ready-made exterior finish. And then you have different kinds of foam core that you can put inside those. So they're structural skins on both sides. Whether you have structural skins on both sides is a key to how they can be used. If you have drywall on one side and it gets wet, it doesn't have any structural strength. So you have to have 2 layers of structural material that aren't humidity-based performance to have a structural span. I think they rated SIPS with OSB and drywall for a 2-foot span, so pretty limited. And the other advantage of a double-sided structural skin is that if you attach the inside skin to the framing to hold the panel in place, you get better diagonal bracing and you get less thermal bridging. A lot of these SIPs are attached with, 12-inch long railroad spikes. I was going to bring them, but I didn't think passing it around here was a good show and tell thing. But you can use long screws, long nails, and I'll show you some pictures later of what that looks like on a frost pattern roof and infrared. So I like to attach the inside skin to the structure rather than using a long through panel. I call it full depth fastener. How are they installed? So here's the basic steps. First, you cut them to fit the building. Usually that's a timber frame or a steel structure, and you have to cut them to the right size, and you have to make holes for windows and doors. Second step is to install light framing, and light framing could be the rough opening around a window or around a door opening, can be the bottom and top of the panel. It can be outriggers to carry a roof overhang without wasting panel on an overhang. So if we have a light shelf or an outside extension to the roof to shade the wall, you can carry that with light framing instead of having to carry it with expensive insulated panels. And then you install termite shield. Foam is a great place for critters to live. It's not really a food sustenance thing for them, but it's a place that they can nest and make a home. So I always put termite shields under the bottom of the panel, because the bottom can be either have a wood light framing member in it, or it can be just bare foam. Depends on the design. And then after you put the panel joints on, which often includes a crane because these things can be pretty big and pretty heavy. Then you attach them to the frame, and then you foam the joints, and I recommend foam, and I'll talk about a lot about that. I like full depth panel joints, and that's the answer to Joe's original question was, those joints have to be sealed through the entire depth to be durable and to eliminate the convection spaces between the panels that are sort of inherent to having panels with a space, intentional space between them to make a sealant joint that will work. And then you have to make sure that that you really get those completely filled. And some of the panel design, well, I'll talk about the other panel designs later, the ones that I don't like. So this is cutting a panel. You can cut these on one side and then the other if they're double skins and cut them to fit, or you can have a big skill saw or reciprocating circular saw, sorry, and you can cut them in one cut. This is how you route the edge of a panel. The bottom right side is after we routed a panel, which gives you either a 3/4 inch depth or an 1.5 inch depth for construction grade spruce. These panel thicknesses, if you bought them stock, are usually 5.5 inches or 3.5 inches for the core to match the standard framing sizes. If they made a 4-inch core or whatever, you had to rip down 2x6s to make a 4-inch piece. And that router is a big, dirty process. You know, you're removing a lot of material from the edge of the panel. This is what I mean by light framing at a rough opening. So you put 2x4s or 2x6s or whatever size for the amount of R value into the rough opening, and you use that to, number one, carry the load from the inside skin if it's fastened to the framing, to carry the window or the door, and also to give you nailing for the trim. So that's what the light framing there is for. And the router can be set to 3/4 or 1.5 inches for different, if you're gonna put two panels together with light framing between them, you want 3/4 of an inch, so you have 2 3/4 equals 1.5 inches, and or 1.5 inches if it's going inside like this drawing shows. And this is a shop drawing showing the outriggers for the overhangs for shading, and they're let into the edge of the roof panels, and if you put two of them together, you get 2 outriggers. This is an example of one of the projects I worked on. This was, it doesn't say when it was, but I'm guessing this is in the 80s. And there's two takeaways here. One is the termite shield, that's galvanized or aluminum, either galvanized steel or aluminum. And that is there to keep penetration from the bottom by termites. I grew up in Pittsburgh, Pennsylvania, and there's a lot of termites in Pennsylvania, and it's required by code, but it's not required up here, but we use them anyway. So, and the other thing you can see here, and I don't know, can you see my cursor? Now you can, okay. So here you can see a gap between these panels. And when I did a set of shop drawings for a panel layout, I always allowed 3/4 of an inch between the panels for 2 reasons. One is the frames were never perfect. They were always either out of square or they weren't exactly the right spacing on the framing members and so forth. And the panels were never perfect because, you know, they're made and cut by people in the field. So, yes, sir. You mean on the roof framing? Oh, yes. Yes. Then build it that way. Okay. I mean, you know, I did exterior masonry systems all the time, and some engineers I wanted to let the brick hang over because the architect designed it with zero room for the foam, zero tolerance on the spray foam thickness behind the brick. And the Brick Institute says you got to have 2 inches behind the brick. So to get some space, we moved the brick out over like this, and the engineers wouldn't allow it, so they had to either make the building smaller inside, or they had to provide some kind of relieving angle at that location to carry the panel. So these panels, you can't, if you put the 2x4, the light framing in the bottom of the panel, it can extend over. And remember, I'm suggesting that you attach the inside skin to the frame, not the outside skin, and not long fasteners that can droop and bend down when you put a heavy load for a sliding glass door or a whole row of doors, yes.
Structural guy we work with, we do 2-foot overhangs with SIP panels, no problem.
Andy said, you can go. Yeah, okay. Mark said he needs a new structural engineer. Okay, so the other thing you have to have is the tree branch on the ridge when you do a timber frame. This picture is courtesy of Vermont Frames. They're a local timber framer, and they also make their own SIPs. And this is how they lay it out. And I think the critical takeaways from this one are, see if I can get yeah, okay. So this is a piece of material that gives you a space so you can slide the gypsum up inside that space, and you don't have to flat tape around the edge of the gypsum board. When you get to the frame, you can go behind it so you can, whatever. And we always painted the gypsum before we put it in, so you didn't have to cut the paint in when you painted the inside. So the other thing I'd like to talk about on this slide is, you can see, I hope, there we go. So this timber frame post sits on the deck. And you have to solid block under a post like that down to the foundation to carry the loads. But they have the SIP panel sitting on a 2x4 at the bottom here. And that's on top of the floor deck, and then the panel goes down over it because they routed out the bottom of the panel to fit over that. And the problem I had with this is, now we have to insulate the rim joist. So my detail, which you saw in this one, the SIP panel goes down by the rim joist, and it covers so you don't have to spray it on the inside. And you can do the wiring by drilling straight through the rim joist and then making your connections inside in the basement. And this is those 2 details. You can see the SIP on top of the floor deck. Sorry about this, a little clumsy for me, but here, and here's, if you get it, excuse me, all the way down by. Lunch was very good today. So, and then, so if you put the SIP on top of the roof deck, these chases, you can see some people made SIPs, if they're laid up with glue, you can put pre-routed chases in for wiring. Okay, when we made foamed in place SIPs, we would put the wiring in the joints where they go together, and if we needed to go over to an outlet, I have a 3-foot piece of rebar with a 1-inch drill bit welded to the end of it, and we would just drill holes over horizontally to wherever the junction box opening was. But this particular panel has 2x4s in the middle, so they were effectively building a stick frame house and pre-installing the foam. So this is really a prefab standard construction, and with wiring chases in it. And then this is, if they put the wall on the deck, this is how they got the wires down into the basement. And if you have an 1.5 inch thick rim joist, you have to stay to the right side, or you're just going to drill down into the rim joist. And to me, going all the way down with the SIPS panel to cover the rim joist is the best approach. This is in the bottom right of this picture, you see it's pretty small, I know, but the bottom right is just a regular electrical plan, so that this says you get the owner to agree to where all the outlets go, all the switches are, and then the shop drawing for the SIPS themselves is on the left, and that tells you where to put the outlets, openings on the panel, each panel, because they come in a big stack, and a crane sits them on the site, and you have to cut them so that when you put them all together, everything's in the right place, including sometimes half a window in this panel and half a window in that panel. And why can they perform better than conventional construction? And this is somewhat rhetorical in that SIPS provide continuous insulation on the outside of the frame. So if you build a frame, put all the insulation outside, you easily meet the code, because you're meeting the code with not only the continuous insulation, you could even use steel studs with this, but you'll still have an R30 wall or whatever thickness of foam you use. It's faster overall installation. I'm going to show you pictures of case studies where we installed the entire building enclosure in 2 days. And then better quality assurance of the foam in the factory. And then that's a controlled environment. And we did a lot of buildings where we ordered the panels, 2 months ahead of when the structure was ready for the panels, but they were made and fully cured before we got them and before we installed them, especially if it was 20 below zero outside. Okay, so this is an example of that. This is a 2-day enclosure project. The picture in the top right is a picture of what the frame looked like with before we started. On the left was as we finished. You can see the lumpy foam at the panel joints. The walls have been foamed, but we trimmed that with a tiger saw or a reciprocating saw, trying to leave the brands out, with a long blade that you can get flush with the material. You can see some of the panels, like, see if I can get over there. Yeah. This panel has part of the window in 2 panels. In fact, they all do. This one happens to all be within the panel, but this is why shop drawings are so critical for these kinds of projects. Another 2-day project. And where I have the red arrow in the bottom left picture, this one is showing some rafter tails to carry out an extended overhang without wasting insulated panel. You can also see that here's the door opening, and the bottom of the door opening is well above the foundation. That's because I'm covering the rim joist. And here you can see the foam in the panel joint before it's been trimmed. Another picture, and as you can see here, you need a crane, especially for the roof. I'll show you some unusual cases where you can do it mostly manually without a crane, but it's rare. But that's what makes it go fast too. So here's a case where we painted the panels before we put them up so they didn't have to cut in and paint after the fact. And this picture on the bottom left is a job that I installed in 2017, and that's the it's 31 years before I took this picture in 2017. So the roof is still performing perfectly 31 years later. So next. This is an 1800 Barnes adaptive reuse, so to speak, and we took the siding off this barn, dug out a space under it, put it up on big I-beams, and then built a foundation, put it back down on the foundation. Spent a lot of time cleaning the guana out of this barn. It was a big deal, and getting it so it would be, because we're going to make a tight building here, we wanted this to be good indoor air quality, and getting all that stuff cleaned off and the beams really in healthy condition was a big deal. Yes, sir. The barn? Making big enough joints between the panels so they could tolerate that tolerance in the framing. And the foundation, we measured, of course, measured the frame and made the foundation to fit the frame. It wasn't like we had an existing foundation there. This was, you know, this barn sat on 10 stones when we first got it. So it was, you know, it wasn't a precise thing. I think I'm going the right way. This is, as the SIPs were being installed on the left side, you can see we hadn't cut the window openings yet. It was very cold when we did this project, so we were happy not to have the windows in yet. And I think the other reason was, do you remember what the windows were? They were early triple glazed.
They were quad glazed with hurd insulate.
Quad glazed with hurd insulate. 2 layers of heat mirror. And this is in 83 and 4. So yes. Well, that happens in the factory with a SIP. And the factory should cure it. The factories have ovens and hot rooms to cure the foam. And if it's glue, you know, they do it as long as the glue requires. But I've never seen the SIPs fail per se, and I've worked on hundreds of failures. The SIPs don't fail, it's the joints. It's all about the joints. So we'll talk more about that in a little bit. But this particular building, you can see in the bottom right picture, they actually installed the wall SIPs here without a crane. And, you know, they had staging on the outside and guys on the inside and the outside. And these weren't that big. These were only 8-foot tall SIPs. So this was not a big deal. We sprayed the attic, so that was not a problem with that needed a crane. This building, and I want to definitely point out the top left picture here. This is Mark's central heating system design. I don't know if you remember that. Yeah, but I'm just making the point that the computer system in this building and the lights were 100% of the heating load. You put a clock as a backup on the central heating backup system, and it never ran. So this
heat pump system, and it takes out of the central computer room and puts it around the perimeter. You put an electric boiler in there, which are cheap, and it never ran.
Everybody able to hear that? Okay. This whole room full of computers in 10 years later was 3 desktop computers on folding tables in the same room.
Yeah, they were decked mini computers.
So what Mark said was that it's a heat pump, heat recovery system, recovered the heat from the computers and from the lights, I'm pretty sure, also. And he put a boiler in, electric boiler, which never ran. So, and the blower door test result on this building after the windows were in, not when it was just without the window holes, was 0.06 CFM 50 per square foot of shell. So pretty good for 1984. This is just some inside pictures. The SIP panel joints, you can just see the seams. If I'm on the wrong, okay, yeah, you can see a seam right here. So these SIPs were made with MDO, and someone here is with the company that made these SIPs. They don't make this anymore with MDO as a one-sided skin, but this kind of SIP was used for this, what they called signboard, and that was 3/4 inch thick material, not 1/2 inch or 15, 30 seconds or whatever 1/2 inch OSB is. So, but this was a totally acceptable interior finish. It could have been sheetrock, but it wasn't necessary. Okay, so SIPs and nail base can be vented or unvented roofs. Can be installed on timber frame construction, installed on steel frame buildings. And I have a lot of commercial building projects that we're not showing because we're trying to target commercial, residential here. So, but it can also be installed on stick frame. So I really like the stick frame solution because I like to use the thickness of the standard framing for wiring and plumbing and other, even ductwork. You don't have to put insulation in the stud bays. You can just, and you put all the insulation outside. You don't have thermal bridging, and you have plenty of room for flexibility with wiring and utilities. Some companies like Vermont Frame make structural panels that basically are the structure of the building, and they're basically just putting the insulation in for you instead of building it conventionally. And you can use SIPs when reversibility is required. I deal with a lot of hysterical organizations that, that's my way of saying historical, that want you to be able to make everything go back to the way it was when it was original. So this is the 20,000 square foot New Hampshire Hysterical Society building in Concord, New Hampshire. And the bottom right is the uphill side of that building, and the top left is the lower side. The whole bank from where you can see these stones in this plaza at the top of the building, from there down is the water is just running out of that embankment right into this building, and there's a brook running through the building. So the way that we built this building, we put these are SIPs that we put on the inside, spaced away from the masonry wall, and the masonry wall is in a straight line like this drawing shows. And at the bottom of this space between the SIPs and the masonry wall is basically a brook, which is a big, wide, cast-in-place concrete gutter system that carries the water out to the river. So these SIPs were all prefabricated. We were allowed to spray foam on the bottom of the floor deck right here. That was the limit. and we were allowed to spray on the steel frame, but we weren't allowed to spray on the foundation wall, so we installed SIPS here. This is a custom panels. What they had on this building for architectural reasons was they had much longer spans than a normal SIP could span. So we made custom SIPs for this project with stronger framing, light framing in it. Where necessary, not all the spans in this were more than 4 feet, but where they were, we put in bigger framing sizes and injected the foam in the panels. So this on the top left is the panel deliveries, and they're all wrapped and ready, and we ship those from Vermont to, this is in Maine. And on the bottom left, you can see some of the panels in and some not in. Those were the longer span panels. And this is what it looked like from the inside. And so that's examples of, sorry. On the bottom left, you can see examples of the finished house. This is right on the Maine coast. This is stick frame walls with SIPs on them and timber frame roof. So you do have flexibility here. And the vertical boards were on the SIPs when they went in place. This is in Woodstock, Vermont. Excuse me, this is stick frame construction with SIPs on the outside. And on the bottom right picture, you can see they've got plumbing in the walls. They haven't wired this yet, but total flexibility on mechanicals and continuous insulation everywhere. This is actually a remodel, and these SIPs are attached to the rim joists and the framing, the framing, last framing rafter on the roof. And on this particular, this isn't a window opening, that's a microwave opening. So because we had the wall thickness to work with, we actually set the microwave back into the wall, and so it didn't stick out as far over the range hood didn't stick out as far. So anyway, you can see all the wiring and so forth in there because that was a stick built. This is another adaptive reuse. This is a very old barn. We stabilized the foundation, and then we put an apartment in this, and the goal was to not have it look like we changed anything as much as possible. And we knew that the water was going to keep coming through the barn boards and running down like it did before we started. So we built this building with a drainage plane between the outside walls of the conditioned space and the original barn board. We didn't touch the original barn board except where we put windows in. And this is on the top left, you can see we built a floor. Below that is where the tractors and the animals are. And the panels went on the perimeter of this loft that you can see finished on the right. And so that's another adaptive reuse where you put the panels away from the original exterior so that you can manage the water on the outside. So what are the problems with SIPs? Well, this is typical for all construction. If the roofing or the flashing leak, the panels are going to get ruined, and that'll be a failure. Another one, is air leakage. And you don't have anything leaking through the OSB in the middle of the SIP. You only have air leakage through the joints. Convection within the panel joints, and if the panel joint is empty, then you have an airspace that's as deep as the panel by whatever your tolerance space is between them that I would use for a a sealant location, and then you have thermal bridging with fasteners. So the causes of air leakage are no sealant at the panel joints and improper processing of the foam sealant. So if you put foam sealant in the panel joints and you misapply it, it won't seal. And I'm going to show you some pictures of why. This is one of Joe's projects in Colorado, and you can see the melt pattern under that red arrow. That's the panel joint line. Correct me if I'm wrong, Joe. Thank you. And thank you. And all those little things sticking out are fasteners, right? Those aren't those are to prevent the snow from sliding, right? Okay, I was kidding about the fasteners, but so the other thing that I found very interesting in Joe's report was the use of dark shingles over an unvented SIP assembly manufactured with an EPS core was part of the problem here. And I would think that that would depend on the R value of the panels. If you have a high enough R value, you probably could get away with dark shingles and not have that be a cause of a SIP failure. But if the SIP R value is marginal, I would think that would be important. So then the other potential problem with SIPs is wiring them. You know, you don't have, if you're not putting SIPs on a stick frame, then and you have them on a timber frame, it's harder to run the wires. And shop drawings are, yes, Peter. This one?
Yeah. Counter such bullets as that, you might have been in better shape this kind of thing.
I think it's all about the total R value. So if you had 4 inches of polyurethane and 4 inches of XPS or EPS, the answer would be yes, because the R value would be lower. Yes.
Or
But the problem is the higher temperature on the surface causing a building enclosure failure. So and
but it's fun, Luna, yeah, not nearly as strong as bond between the foam in place.
correct. That is correct, but whether the glue joint is tolerant of a temperature above 150 depends on the glue and the foam. And I think there's some case where EPS does have more dimensional stability problems than polyurethane, so higher temperatures would impact that.
Bouncing along that one edge, not where that
Now let me point right here. Oh, over here? That's because it's under an overhang for that dormer. So there wasn't, you know, there might have been 2 inches of snow there, not a foot. So it melted off quicker. Good questions. Okay. Yes.
Yes. Do you know what the fraction was of that poundage of the EPS? Was it 1 pound, pound and a half, 2? They think that.
This is all I know about those panels. So, yeah, well, that would affect the dimensional stability, which is, I'm guessing it's below 2 pounds. Yeah, agreed. The question was, do I know the density of the foam? And the answer is no. It wasn't in the report. Okay, so the wiring's more complicated. You need an electrical plan and shop drawings, and the roof SIPs require a crane. Just more examples of SIPs going up. Pardon me? If you couldn't hear, the fix was to put a vented over roof on it.
Yeah.
What I did on my commercial jobs, and I could skip ahead to, I have some commercial case studies after the ending slide. We'll see if we run out of time. But I used to inject the vent space on a vented roof full of closed cell foam. And that added R value and eliminated all the air leaks at the joints because it filled them in from the vent space.
Westford School.
Orford School, that's the project I have. So Mark and I both worked on a project where it was nail-based panels, 2-inch vent space, and the contractor claimed that the vent space wasn't big enough. It was, 2 inches vent space. And I put theatrical fog in the soffit and it came out the ridge and proved that that wasn't true. And
Because they never did any air conditioning.
right, and then we put theatrical fog in one of the classrooms and it came out through the shingles and the ridge vent also because there was a acoustical metal deck which is perforated with a layer of polyethylene on top of it, which when they put the 16-inch long screws through, they wound it all up under the SIPs, under the nail base, and made big lumps with no air barrier in between. So, anyway. So the problems here can be superficial caulk, I'll show you pictures, pre-applied sealants, that would be Vermont Law School, where they put the sealant on the edge of the panel, took it up with a crane, set it in place, never perfect the first time you set the panel down, slid it up, slid it down, took it back off, put it in the right place, whatever, and the sealant is ruined at that point. So. And then blind injection of joint spaces. I'll show you some details. Some of the manufacturers require you to drill holes and fill them all blind so you don't know if you ever got them. And whoops, splines. Change it. Splines, a lot of panel manufacturers recommend splines. The splines are not an air barrier. And they don't work at all in changes. So if you have two SIP panels in the same plane, splines might work, but when you put them at a ridge or some other change of plane, the splines you can't even put them in. So, and then the last one is gaskets. Most industrial metal panels have gaskets, but they don't work well on wood construction. And unless you're doing something in Antarctica and you have a way to compress the gaskets. And I'll show you a slide about that later. So joint seals, I recommend are full depth, and I recommend a 3/4 inch gap to give you tolerance for the frame deviation and the panel size tolerance. So that's, and I like to seal, attach the inside skin to the frame to carry the load better and help brace the frame, and also to eliminate thermal bridging by using short fasteners, not long ones. And filling the joints also eliminates the micro ducts, which is what Joe calls them, and I call them convection spaces, but
So if you want to fasten it through the inner skin, does that mean you got to drill a hole all the way down through there with a, an inch bit or something, and then put a screw in and then fill the hole?
I'm going to show you two methods, but he just said, do you have to drill a hole to screw the inside skin in directly? The answer is yes. Or you have to route the edge of the panel so you can nail that inside flange as you put them in place. So how to detail them. And we're going to talk about in the same plane, at changes of plane, at rough openings, and at penetrations. You've already sort of had glimpses of these, but transitions in the same plane are pretty easy. This is these are panel manufacturer drawings that you can't see it yet. Sorry, that have splines in them. And in the center here, you'll see they call this little reglet a foam channel. Okay, here's the foam channel. And you're supposed to drill a hole in this through the spline, through the skin, into that channel and get it all. Okay, and no way to quality control that, at least not visually. So my recommendation is a space between the panels, and that you can both fill full depth, you can see it so you know it's full, and you might have to trim it. Yes, sir.
Drill the hole and then put the foam in until it came out the next hole. And the infrared camera, it looks pretty darn good.
Did you fog test it?
Like fog tested, but we did take 9 inches wide, team top and bottom.
Okay.
That keeps growing quite great.
Okay. So you can, I would consider some of what he did heroic measures. If I was pardon me? You're very welcome. You're a hero. And if you have an open joint, and I'm going to show you one reason I like it is in retrofits, we make that space between the panels after the fact, and we use a chainsaw. So you can't do that in a new install. It doesn't matter. It's where you drill the hole and put a bolt through it so you don't go through to the inside of the building, because that controls the depth you can clean out with your chainsaw. Okay, so again, this is just in the other plane, these details. And sometimes they'll put a piece of 2x in this location, and you're supposed to put caulk on that piece of wood, drive it in place, put caulk on the next panel and put that in place and make a good seal. I don't care how you do it, frankly, as long as you quality control it. And I like pressurized theatrical fog because you can do that any time of year. And it doesn't matter how long it's been since you put it in place. So but I think this is the ideal panel joint. The reasons for the splines are typically to line up the skins. And if the panels are bolted or screwed or nailed to a timber frame or some framing member or a 2-inch tongue groove wood deck, they're not going to be out of alignment. So I think it's a one-size-fits-all attempt by the manufacturer to cover their backs on any possible substrate condition. But this panel joint that I have in the detail it doesn't require alignment of the skins unless the panels are so far out of plane that you have to try to force them into alignment, and you have to break the bond between the foam and the skin in order to change the plane of the skins. Okay. This is one, if you have to have one spline, you can do it. You don't get quite a full depth, but almost full. This is the one that Andy was talking about, or one of the two solutions is to make the gap between the panels only through the foam part by routing it out wide enough that you can get your drill bit extension down in there and screw the panel to the frame. And then you fill that whole space with foam sealant. This is the other one that Andy mentioned, which is drill a hole in through the first layer of OSB and the foam, put the fastener in place, and then fill the hole with foam. If you're foaming the panel joints, filling those holes with foam is pretty simple. It's not a big deal. And I'll show you some examples of that. This is what I call a convection gallery, where the panel joint was sealed superficially only on the surface. In other words, at the OSB level. There's a big airspace under that. And this is over a swimming pool.
Great.
And under these nail-based panels, there was conduit and all the outlets for the ceiling fans and the swag lights and everything else. And they were all connected. So it only took one of those holes to leak for all of these to be getting indoor high pressure, high humidity, at least 80% through all these joints. So here's changes of plane. You've got ridge, you've got wall to roof, and you've got foundation to wall. And this is the kind of joints that the manufacturer recommends, where you take one panel, put a bead of caulk or 2 beads of caulk on it, put it in place. And you have to get this in the right place the first time. And there's no tolerance in this detail for the building or the panels not being exactly the right size and shape. So this is my recommendation. You leave a gap and you fill that gap with sealant. You get tolerance on the frame and the panels. This is an outside corner detail, 2 different options for that. And I like having, I went by too fast, sorry. Okay, so I like having this gap in the right picture here for the foam sealant. And I don't care which panel goes by, that's part of the shop drawing. This is wall to roof. The panel manufacturer recommends, again, a tight joint with perfect carpentry and perfect frame shape and size and perfect panel shape and size and no room for tolerance, and foam tape. I'm not sure what that is, but you can do the detail on the bottom right, which is a much less fussy panel cut and a very open and visually quality controllable detail for sealing the joint.
Great. So I think this is a good time for you to say what we saw at Oak, where the seal was that reglet. And so even if that seal was perfect halfway up the roof panel, the bottom half of the panel leaks to outside. And we did the fog test and every single joint leaked.
Yeah, I do have pictures of that.
Okay.
I'll go to that if time allows, and I'm hoping it does. But it's sort of like corrugated metal roof deck. If you seal just under the deck, all the flutes on top of the deck are still open to the outdoors. Remember the Dartmouth mock-up? Anyway, yes. Okay. So here's a ridge detail. The ones on the left again require 0 tolerance carpentry, And the ones on the right are both easy to build and more reliable because they're visually quality controllable. Probably the bottom right one is better in terms of having nailing right up to the ridge. But the one on the top right, even though there's probably 3 inches from the ridge with no nailing, most ridge vent covers are nailed well below that anyway. This is a valley. Again, I would make a bigger space to allow tolerance. You know the valley is even going to be harder to build perfectly than a ridge. So all these angled V-shaped panel joints, I think, are difficult to build. And transitions at rough openings, again, you need to seal these in place in a way that is verifiable. Again, you can do it afterwards with pressurized theatrical fog or infrared or whatever you want. But if you do it as you go, it's easier and you don't have to keep going back. This is how they recommend, the top left picture here is how they recommend sealing a space behind a light framing at a rough opening. The problem with this is you need a tool that can make a space that's bigger than the light framing to allow room for the foam. And I have never seen a tool that could make more than 1.5 inch route in the edge of the panel. This detail would require at least a 2-inch route to have any tolerance at all. Again, foam sealant. Foam sealant, first of all, if you're going to use foam sealant, you want to use expanding foam sealant. This is not a window and door application where you don't want to push. This is an application where you want it to flow out into all the little voids and fill everything. So you want expanding foam sealant, not a non-expanding. Next thing is fasteners. Fasteners are a big deal because of the thermal bridging. And I'm going to talk about 4 different methods. You can see that, I haven't gotten to that. I'm getting confused, sorry. You can see this panel is ready to go up on the crane, and they start the fasteners on this panel, so when the guys up on the roof are working, those 2x4s on the top are basically staging for the roof, guys up on the roof, and they're gonna put 7 screws in every horizontal attachment point and at each row of the framing. That's a lot of screws. So here's what you see in those kinds of situations with thermal bridging through the fasteners. And this is Rivendell. So that's through the nail-based panels that Mark and I were talking about earlier. That's a different project, but that's also what it looks like. Now on the right is a method that was developed by Northern Energy Homes way back in the energy crisis. And they had styrofoam glued panels, and they used truss clips so that they could put 1 screw to hold four panels in place. And they screwed the clip to all 4 panels, but they only had 1 big screw that was through the whole assembly into the frame behind it. So this is a compromise better than, it's in between lots of thousands of full depth fasteners versus hundreds of full depth fasteners. So it was better. Are you talking about this particular project? Oh, they had the wrong size opening for the window. So they put the piece of foam back and then cut the right size window hole. That was an installation error when they were cutting. They probably didn't have shop drawings, and so that was a construction error, but they just put it back. And I don't know how they attached that. This was I came to this because they had a panel failure, and this is after I had them strip the siding, because basically the whole wall in most of this situation was rotten OSB. And I'll show you more pictures of this project later. This is after we cleaned out the joints with a chainsaw. And you can see at the bottom of that, you can see the tongue and groove boards. And remember that those will leak foam. So you have to cover everything downstairs, or put something in the bottom of that panel joint gap to protect the building by sealing those joints. The top of this, we had temporary weather protection, and that was folded up over the ridge. But you can see the moisture damage. This is the shape of the moisture damage, and that's what Joe calls ridge rot. Okay, and that's in line with the panel joint. And I'll show you more of that later. This is one of the projects where we used what I called the nail tab, where we fastened the inside skin by making the edge route wide enough to fasten the inside skin directly. And you can see what we did was, because we made the joint so wide, I put strips from one side or the other of that cut in the middle, and foamed them back in place, so I had nailing between within the panel joint width. And you can see, you get the cursor to the right place here. So we had a strip of OSB from the replacement piece in the middle of this 3-inch wide gap. We only did this method once as a trial, but it worked. It worked great, and it performed well, but it wasn't worth the effort, frankly. But so we did on later projects, and I'll show slides of this. We drilled the holes and filled them. So that's what it looked like being foamed in place. You can see in the bottom right here, that's what I called the nail tab, and that's what's attached to the frame. So this was 3/4 inch OSB, so it was very, very rugged. That's what the detail of that would look like. Now this building has the holes drilled. So everywhere the red arrows point at, we drilled an 1.25 inch hole, put the fastener in, and then just shot a foam in it when we sealed the panel joint. And that's what the architectural detail would look like in plan and section. Yes. Back. This is custom panels, which means they wanted this with long span framing and the wiring already in place. So these panels were made that way, and because I could foam in place, we framed them up and filled them. And they went up in, a day. And in order to attach, we're putting the fasteners in where the framing is behind it. And there's enough framing to support the entire panel, and the panel joints are at a framing member. They're not out in midair. real quick, this is the Ways Divide in Antarctica. And this is my comment on gaskets. In order to, this is actually at the Cold Regions Environmental Lab in Hanover, New Hampshire. And we made, this is an autonomous weather structure that was the first autonomous structure in Antarctica to send weather data out year-round without somebody there filling the gas tank all winter long. So that's what they meant by autonomous. The design goals here were it had to stay 70 inside while it was minus 70 outside with no solar, 70-mile-an-hour wind, and with a 20-inch wind generator. So like a window fan sized wind generator. And when they opened this in the spring, it had to go to the site in a helicopter. And I'm talking about a two-seater, not a military helicopter. So we had to design this so that with gaskets, because they couldn't do anything at minus 70 with sealants and caulks and that kind of material. So this was all gaskets. These were gaskets that the University of New Hampshire Aerospace Department developed and that we installed on these panel blocks. And when they opened this in the left corner in the spring, they said it was the first thing they've ever opened up after a winter that wasn't full of snow. And it stayed at 70 degrees inside. And this you can just barely see it here, but this is the top of an all-sky camera, which part of the weather data that they sent out was a picture of the sky. And that was a 360-degree acrylic bubble on top of this that was part of the load. And the other thing that made this hard to do, if I can go back, doesn't want to go back, was they have lots of wires running out of this for all their electronic equipment and monitoring and so forth. And they had weather equipment, and every one of those penetrations had to seal, and that was another design problem. I'll just leave it at that. But we tested this at the Cold Regions Lab in Hanover before it went to Antarctica. This is how the blocks were made, and there were no through full depth fasteners in this design. As you can see, you can't see because I have to do it here. Okay, so this is a threaded rod that pulls the panel block down tight on the one below it and compresses the gaskets this way. And this little circle right here is the threaded rod running in the other direction that pulls them together so the end gaskets are compressed. And that's what made this work. The original design had shiplap, and we screwed through this way. And even though they weren't completely full depth fasteners, they were still a thermal bridge, and they didn't seal well at the butt ends. So gaskets, it's hard to make them make corners. So that was takeaways from this. But these are not, I mean, you could build buildings with this, but they're not readily, you can't buy those panel blocks anywhere. I don't know why. I think they're a great idea, but anyway, it'd be nice if everybody could build their own houses with them. And if they just have two more kids, take down a wall and use the blocks again to build the next extra bedroom, and but anyway, that's another project. So this is a paper that Joe did on panel joints and ridges and ridge rot, and my experience with panels is that the gallery at the panel joints makes an airflow convection space, And he's showing that kind of details here. And that's the same thing that I've seen. Here's a melt pattern from his original roof. And exactly, that's where the drinks are. So this is more ridge rot. The bottom right one's a pretty good example of that. And this is another, is this your project or, I think that's mine, yeah. And this is where they had never sealed the slope at the ridge properly. You can see the big gap. This is Joe's diffusion port, and he has what he called micro ducts along each side of the strapping, which is the strapping is actually running up and down here. And there's because of the tolerance between the foam or possibly the shrinkage in the foam, you have spaces there that are conducting. Somehow those must be connected to the inside, right, Joe? Oh, okay. All right, this is the timber frame project that the foam failed, not the foam sealant failed, not the panels. So nice, beautiful place. You can see the timber frame panels being installed with a crane. And here you can see in infrared in the top left, these are big white patterns of frost. So this is warm, moist indoor air coming out of the panel joints and painting the leakage onto the underside of the soffits. And you can see this whole soffit down here is completely white. And you can see frost coming out of this joint. And so these are all pictures of frost. You can see the frost here and the frost all the way along. Here's infrared showing all the leakage. And these guys thought they did it perfectly. And I asked them, I said, where did you keep the cans? This was single component. I said, where did you keep the cans while you were working? And they said, on the floor in the pickup truck. And I said, and what did you do to the panel joint before you put the foam in? And they looked at me like I had 3 heads. And I said, well, what does the can say? And they got this was the next year, so, but I had some cans with me, and I showed them, and it says that you have to mist the joints before you put the foam in. Misting the joints means you have to add water. And the reason is that one component foam sealant is water cured. Okay, so you've got isocyanate in there that has to react with water for it to set up. And you have to have the chemicals at the right temperature, and you have to shake the can. So another case of if you don't follow the instructions, you won't get a good result. And the other little detail here, you can see this panel joint in the roof, and you can actually see a little bit of this one. Again, the sealant didn't work. So this is from the can. This is our most misunderstood introduction. You only need an ounce of water to properly cure the entire can of foam. When you foam a deep void, so how many of you have ever sealed a window? Everybody, right? Okay, if you have a window weight pocket, which can be the thickness of the wall by 4 inches, that's a pretty big void for foam sealant, okay? What you're supposed to do is put a layer of foam in that void, mist it, put another layer of foam in that void, put some more water in, because you won't ever get water through the entire body of the foam to the material in the middle. So you have to use water, and you never do a joint, thank you, without it being at least 55% outside. So I took 2 Ziploc bags, I shot the 1 can into both bags. I closed the bag on the left, the Ziploc baggie, I sealed it shut. The next day, that bag was back to liquid, and the bag that was open was foam. So what's on the left, which is the original liquid that was in the can, is what they had in all those panel joints in that house. It was just gummy. So you also have to, and a lot of guys will take an almost empty can of 2-part, and they'll want to finish off the one that's not quite empty. So they'll have a can that's full and a can that's empty. The pressures that are in those cans are critical to it being on ratio. You can't use an almost empty can with a full can because they won't be at the same pressure. And the chemicals have to be warm, so you have to have more than your pickup truck worth of heat to get them warm. This is just a typical cooler. I use waterbed heater because it's got a temperature control, and I know I won't blow the cans up if I overheat them with a light bulb. And if you have a 2-part kit, you can use a bigger toolbox. And this is the chainsaw method. And he's cleaning the joints out. This is the swimming pool building with all the gallery spaces. This is a foam, EPS foam panel project that failed. And you can see here they have a post every 4 feet, so that's the panel joint module. And this is what it looked like underneath. This is rot at the soffits. And they had not sealed these joints at all. You can see in the bottom left detail there. And this on the right is one of my test holes. So what we did was we removed all the, what I call Wheaties, which is the disintegrated OSB, and dried it all out and sealed all the joints. And then we glued new OSB on and attached it. There's the Wheaties, and reattached it with panel joint similar fasteners and new glue. And we were able to put this back together. This is the roof and the joints after they were cleaned out. Did a little mold remediation along the way with some Kills type of paint, mold killer material, and glued new OSB and sealed the joints and put it back together and made a house of it. This is another ridge rot failure. You can see the dark spot on the top left above the white arrow. That's at the top of the panel joints. Again, chainsaw cleaning out of the joints and the leaks to the indoors, because we had the beds covered, but we had to go up and trim the foam off the panel joints. That's how far apart the panel joints were. And this is an example, quick example of a commercial building, swimming pool building again, nail-based panels with a vent space, but the panel joints had never been sealed. And you can see the melt pattern on the roof on the bottom left. And we filled, they were gonna replace the shingles here anyway. We filled the vent space with foam, closed cell injection foam. And after we were done filling them, you can see on the right, the melt pattern, that solved it.
Yeah. Thank you for that canned presentation.